we shall study about the radiation network. Before studying about the radiation network, we shall define two terms: irradiation G and radiosity J. Irradiation G, as the name itself indicates, it is the amount of incident radiation on a surface. The amount of radiation incident on a surface is known as irradiation G. It is measured in watt per meter square. Radiosity term, another term radiosity J, is the amount of radiation leaving the surface. The amount of radiation leaving the surface, here it is shown in the figure. The amount of energy incident upon surface is G. The amount of radiation leaving the surface consists of two parts. That part which is emitted by the surface on account of its emissive power. The part which is emitted by the surface is epsilon EBA, epsilon times the emissive power. And the second part is the amount of energy that is reflected by the surface, that is R into G, where R is reflectivity and G is the amount of is the irradiation. Therefore, radiosity J is equal to RAG plus epsilon A into B. Suppose we will assume that the two bodies are opaque bodies. Then transmissivity of opaque body is equal to 0, tau equal to 0, then RA will become equal to 1 minus epsilon. Substituting the value of RA equal to 1 minus epsilon A in equation 1, we will get J equal to 1 minus epsilon AG plus epsilon A EB, which gives G equal to J minus epsilon A EB divided by 1 minus epsilon A. This is equation number 2. The net radiation leaving the surface A or leaving the surface 1 is Q by A equal to J minus G. Net radiation leaving the surface 1 is J minus G, where J is radiosity, G is irradiation. So Q by A equal to J minus, substituting the value of G from equation 2 here, J minus epsilon A EB divided by 1 minus epsilon is equal to, we will get Q equal to, on readjustment we will get EB minus J divided by 1 minus epsilon divided by epsilon A. Equation 3. So net radiation emitted by the surface is EB minus J divided by 1 minus epsilon divided by epsilon A. Comparing this with Ohm's law, I equal to delta V by R, we will get the denominator quantity as the resistance, surface resistance, is equal to 1 minus epsilon divided by epsilon A. This 1 minus epsilon divided by epsilon A is known as the surface resistance. It is a resistance due to on account of it the surface property of the material. Now see the figure. Our amount of radiation leaving the surface A is J1. All the radiation leaving the surface J1 will not be intercepted by B or will not be received by B. This is because of relative orientation of these two surfaces A and B, and also relative geometry variation between these two bodies A and B. The amount of radiation that is reaching the body 2 or body B will be equal to J1 into F12. F12 times of J1. F12 times of J1 into A1. the amount of radiation leaving the surface 1 and reaching the surface 2 will be A1 F1 to J1. Similarly, the amount of radiation leaving the surface 2 and reaching the surface 1 or A is A2 F21 J2. A2 F21 J2. Therefore, right here, amount of radiation leaving the surface 1 reaching the 2 is Q1 equal to A1 F1 to J1. Amount of radiation leaving the 2 and reaching the 1 is Q2 equal to A2 F21 J2. Equation 6 and 7. So net radiation at the surface 1, net interchange from surface 1 to surface 2 will be Q12 equal to equation 6 minus equation 7, A1 F1 to J1 minus A2 F21 J2. And since A1 F12 equal to A2 F21, that is a reciprocating relation between the shape factors, we can write Q12 equal to A1 F12 into bracket J1 minus J2. So Q12 equal to J1 minus J2 whole divided by 1 by A1 F12. Q12 equal to J1 minus J2 divided by 1 by A1 F12. Comparing equation 8 with the, again Ohm's law, I equal to delta V by R, the denominator quantity is the thermal resistance 1 by A1 F12. The denominator quantity is the thermal resistance offered between the two bodies. It is 1 by A1 F12 is known as a shape resistance. Shape resistance. Therefore, when the two bodies are radiating with respect to each other, two bodies are radiating heat with respect to each other, we have got three resistances: surface resistances of first one body, surface resistance of the second body, plus shape resistance between the two bodies. Therefore, it is shown here Q12 equal to EB1 minus EB2 divided by 1 minus epsilon 1 divided by epsilon 1 A1, that is surface resistance of 1, plus 1 minus epsilon 2 by epsilon 2 A2, surface resistance of 2, plus 1 by A1 F12, that is the shape resistance between the 1 and 2. The same has been shown with its network diagram or electrical network diagram. EB1 J1 J2 EB2. EB1 to J1, it is a 1 minus epsilon 1 by epsilon 1 A1. J1 to J2 is 1 by A1 F12. Resistance between J1 and J2 is A1 by A1 F12. Resistance between the terminals J2 and EB2 is 1 minus epsilon 2 divided by epsilon 2 A2. Now, we will apply this network analysis to radiation heat exchange between two black surfaces. Radiation heat exchange between two black surfaces. We know that the black surfaces for the emissivity of black surfaces is 1. Therefore, for epsilon 1 equal to epsilon 2 equal to 1, putting epsilon 1 equal to epsilon 2 equal to 1, the surface resistances offered will become 0. Now, the two black bodies radiating heat with each other have only shape resistance. Therefore, Q12 equal to sigma T1 raised to 4 minus T2 raised to 4 divided by 1 by A1 F12 is equal to A1 F12 sigma T1 raised to 4 minus T2 raised to 4. It will be A1 F12 sigma T1 raised to 4 minus T2 raised to 4 for the radiation heat exchange between two black surfaces. Now, radiation heat exchange, we will apply this to radiation heat exchange between two infinitely parallel plates. So, again we have sigma T1 raised to 4 minus T2 raised to 4 divided by, for a infinitely parallel plates, F12 equal to 1, shape factor of 1 with respect to 2 is equal to 1, and area of all the plates are same. So, substituting these values in the denominator, 1 minus epsilon 1 by epsilon 1 A1 plus 1 by A1, because F12 is 1, well, this is 1 by A1 plus 1 minus epsilon 2 divided by epsilon 2 A2 will give sigma T1 raised to 4 minus T2 raised to 4 divided by 1 by A1, 1 by epsilon 1 minus 1 plus 1 plus 1 by epsilon 2 minus 1. This gives Q12 equal to A1 sigma T1 raised to 4 minus T2 raised to 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Q12 equal to A1 sigma T1 raised to 4 minus T2 raised to 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. This is the radiation heat exchange between two infinitely parallel plates. This derivation has already been proved while discussing the while arriving at the proof of Kirchhoff's law. Now radiation heat exchange between concentric cylinders. So for concentric cylinders, for the inner cylinder, radiation heat exchange between the inner cylinder 1 to outer cylinder 2 is given by for shape vector between the inner cylinder for the shape vector 1 with respect to 2 shape vector of 1 with respect to 2 being the outer cylinder will be equal to 1, F12 equal to 1. Therefore, we will get Q12 equal to sigma T1 raised to 4 minus T2 raised to 4 divided by 1 by epsilon 1 by epsilon 1 A1 plus 1 by A1 1 by 1 minus epsilon 2 divided by epsilon 2 A2, just as we did in a parallel plate case. Same here, 1 by A1. Here A1 will not be equal to A2 because it's a concentric cylinders. Therefore, taking 1 by A1 outside the bracket, here in the denominator it will be 1 minus epsilon 1 divided by epsilon 1 plus 1 plus A1 by A2 1 minus epsilon 2 by A2. So on simplification of this, we will get Q12 equal to sigma A1 T1 raised to 4 minus T2 raised to 4 divided by 1 by epsilon 1 plus A1 by A2 1 by epsilon into bracket 1 by epsilon 2 minus 1. This is the radiation heat exchange between the concentric cylinders. This also has been proved earlier. This we are now proving it with the help of radiation network analogy. Thank you.